Okay, so I have like about an hour and a half of material here. I was planning a 40-minute talk. I discovered it was 30 minutes, slightly late in the day. I'll see what I can do. Also, I would appreciate it if people feel like interrupting and asking questions, feel free. And if I don't cover anything that I mentioned in the abstract, absolutely feel free to catch up with me later and ask me. Okay. The purpose of this talk is to describe basically practical project experience with the sort of difficult challenge that we might encounter at work. This is a specific problem we got about a year ago, and I am just going to tell you how we approached the problem and the sorts of things that we did to deal with it. I will say so what's important is that our approach to these problems is defined very much by a probabilistic programming approach, which we use for dealing with these sorts of small data problems. And I was delighted to see that the Stan logo appeared up on the screen in the introductory talk, because our primary tool for these things is Stan, which you can use through PyStan. And because you can use it through PyStan, I'm standing here, fundamentally. But really, this is principally a talk about Stan. Okay, and the methods around that. So, in outline, I'll tell you about the challenge. Look at the data, understanding the data, modeling the data, and extrapolating the data, by which time it will be about 1:15. Okay, so this is the problem. About a year ago, a large pharma company contacted us and asked us basically to build a model that would extrapolate out for the next 9 months the sales of 3 different products in a variety of regions. Okay, the time series, I'll show you them in a second, is short. So everybody talks about big data. My daily bread and butter work consists of exceedingly small data. This data came on one Excel spreadsheet, and it was a small Excel spreadsheet. Okay, there are lots of other points there that I'll mention as I go through. We use 2 basic tools to let you know up front. We start off by using a Gaussian process, and then we move on to using a custom state space model, both of which we solved using Stan. And the fact that we solved in Stan has specific properties which are important. Okay, so here's the data. This is the complete data we got. There's up to been a bit normalized, so you can't actually see what the actual values are. But what you can see is that there are 3 different products in a variety of different markets. So you've got brand 1, you've got brand 2, and you've got brand 3. A fun extra complexity, apart from the fact that you've only got about 70 data points at most, is that you will see that late on in the game, the company introduced a new package of for these products. So I forget what happened actually in one particular case, but I believe, if I remember correctly, this used to be sold as a file, and then they discovered that doctors were opening the file and using it twice, and really to discourage that, they started distributing it as a prepackaged syringe, so you couldn't use the same thing for 2 things. Okay, so what is interesting here is not actually the challenge, an extra bit of the challenge, which I won't really get to today, except maybe if I have a little bit of time at the end, is that you're interested in the underlying trend. You're not interested in these specific lines. You're interested in the combination of the 2. Okay, so you see that for brand 1, you've got 2 trends. For brand 2, you've got 2 trends. And for brand 3, you've only got 1 trend. To make things a little simpler, it turns out to be a good bet, a good choice. We focus on brand 3. That is what we did at the beginning. You pick the easy thing. It turned out to be a serendipitous choice, because if we'd been busy trying to figure out what exactly was going on in these more complicated cases, we would never manage to figure out anything at all. And it turns out in the end that actually these more complicated cases don't make things any more complicated. Okay, so this is the data we've got. What's the first thing you do? You get the data from the client. You open up your system. You have these time series. Okay. The first thing you do, the econometrist's tool of choice, is you run a lowest regression through it. Okay. Now, what's important in this case, well, there are many important things in this case, are that this is a completely standard. The idea at this point is not to choose anything. Okay. You want to use things straight out of the box, making no assumptions if possible. You are trying to figure out what exactly is going on here. Okay. And this is the first thing you do. So you draw the lowest regressions and you get these things. This doesn't actually tell you very much, unfortunately. Lowest is kind of a primitive gadget, but it takes 10 minutes to run it, so you run it, okay? What you can see, now that I've joined the dots together and stuff, is that things start off small, and then the noise gets bigger, okay, as we go along. Which is not really surprising. Down here, they're probably selling 10 units. They've introduced it into the market. And then as they sell more and more stuff, the noise from month to month gets greater. Okay. So lowest is kind of the baseline standard, but we can do a lot better than that. Okay. So what we're going to do is the first thing we do is we build a Gaussian process. Are people familiar with Gaussian processes here? Yeah. Okay. For those that are not, a Gaussian process is a bit like a neural net, only for very small data, with much, much better mathematical foundations. That sounded like a smart-ass remark. I'll actually explain to you what the value of the extra foundations is in a second. Okay. What is important here is there are several talks in this conference on Gaussian processes. I don't know what they're going to say, but unusually, with respect to standard practice, since we build our Gaussian process in Stan, we extract the marginal, not the maximum likelihood. And we can also put in a custom noise model. Okay, so there's lots of stuff to talk about here. So let me talk about it. Okay, here is a Gaussian process programmed in Stan, complete. Okay. I don't really expect you to understand this off the fly. But what is going on here is we are essentially trying, so what we can see, we look at the data and we can see the first question we have to ask ourselves is, what is the nature of this noise? So we've got the Gaussian process is going to attempt to draw a line like the lowest, but it's a much more ambitious attempt to draw a line. But on top of the line, we have a noise process, which we have to model separately. Because we're doing this in Stan in a probabilistic programming language, we can do lots of interesting things that we can't do with an off the peg package. For instance, the first thing we decided was this noise is growing bigger over time. Yeah, so this is a single noise process. It starts off with small noise and it gets bigger. Noise grows, we're going to assume, because it's a reasonable thing, as the square root of the amplitude of the underlying process. Makes sense, yeah? I mean, down here, you're buying one product. Up here, you're buying 10 products. The variance will go up. The variance will go up with the scale. The standard deviation will go up with the square root. Okay. The other, at least nice thing, one thing that we didn't do here is, one thing that we often have to consider is we use non-Gaussian noise. Okay. But in this case, we didn't use non-Gaussian noise because what we're obviously getting is it's plausible to think that we are getting noise from a binomial distribution. So to good approximation, it's Gaussian. What else is there to say? Yeah. What would have been nice and what we experimented with was you could make this line the amplitude of the function itself actually drive the noise process. So you could say, depending on where you are on the vertical axis, that automatically defines the noise process. This will be the ideal, and you can write down a model that will actually do this. Well, you can if you make a couple of other modifications as well, but it turns out that that doesn't work, even though nice though it is. So what we actually did was, rather than have the principle, so here you have a principled, unprincipled compromise made for the purposes of actually getting things to work. Rather than take the noise driven off the underlying process, we looked at the actual samples and took the moving average and used that to define the scale of the noise process. Okay. The other thing we did is, if you use a Gaussian process, even an off-the-peg one of the problems is there are a couple of free variables that you have to calibrate. Yeah? Yes? Yeah, exactly.
To extrapolate.
I come to that later. We're not even close to the extrapolation bit yet.
Yes, and thank you. My question is basically, when a Gaussian process extrapolates into the space where it has no data points, it reverts to the mean.
Indeed, you're anticipating my slides.
Okay.
Yeah.
Thank you.
Okay. Anyway, an important point is that because we're taking the marginal value, we can also marginalize over prior distributions on the free parameters in the model. So, as I said, using the lowest model, we used a parameterless model. And in this case, even though we built the model ourselves, we're fundamentally using a parameterless model. We're not trying to guess a particular value so that we can calculate the maximum likelihood value. We're taking the marginal, okay? Which is what this thing does. Okay. We run the Gaussian process over the data, and this is what we get. This is very interesting. For starters, you can see that the Gaussian process is finding a lot more structure in the data than the lowest regression could. You can also see, and this is what I meant about the extra mathematical structure, that because we're taking the marginal distribution over the underlying process, we can calculate credible intervals for the Gaussian process. Okay, so the blue line is the actual thing, fit, the marginal, and the red lines show the one standard deviation variance in the underlying fit. And of course, you can also see that, of course, the variance goes up as you get up because the noise goes up, yeah, so that the fit gets fuzzier. Okay. So this is what we get. As I said, we see immediately more structure. One of the interesting things is, again, this is an actual work in progress, a project with actual consultants in the room. It's not an academic exercise. So at this point, all I had was this. But I did notice things like this. Okay. What does this mean? And you can see that you can see similar structure in many of in many of these. Okay. So simply eyeballing it suggests that something is going on here that we don't know. And you put this up in the room with the marketing experts on the product, and they say, of course, this is where a competitor introduced another product. Okay, so what you're looking at here is a secular event. This is nice because it shows that the Gaussian process analysis was able to pick this up reliably. On the other hand, it is incredibly bad from the point of view of attempting to extrapolate the process, because this is not only a secular event, it's a secular event right at the end of the process. Strictly speaking, at this point, we are hosed. We can just go home. Unfortunately, you can't go home at this point. So what do you do next? All right. So what we can see here is a nice development of sales. And you can see that, here, this is a secular event. We can imagine that something went on here. You can see that the curvature is here, and also that the noise goes up, which suggests also the same. You can see the same here. So, what are we going to do? As somebody already said, we cannot extrapolate with the Gaussian process. Okay? What we can use the Gaussian process for is to figure out what is going on. Okay? To develop intuitions. Because at the beginning of this, I didn't have intuitions about the market for patented drugs. However, on the basis of what I could see here, I could start to think about a model. Now, you cannot extrapolate a Gaussian process. What looks like a Gaussian process? But you can extrapolate it. The closest thing you can get, or at least the closest thing that occurred to us, was a state space model. Now, a standard state space model is you can build very complicated state space models, but the standard state space models obviously won't work in this case. What you do then is you sit around for a week and start thinking about what exactly happens in the dynamics of drug sales. Okay, so we're going to assume that you introduce a product, it grows, something happens, there's a secular event in the market which is going to change the trend in your sales. It will stabilize on that. It will move forward again. There'll be another secular shock. It will move forward again. So what we had to do then was to build a model of the dynamics of a patented product in a market where competitors were entering the market at varying times. And so after a couple of experiments, what we got was this. Okay, so this is the set of equations defining a state space model for patented drugs, but it's actually pretty general. Okay, what we have are the observations. We've an underlying trend. We've obviously got observations which are scaled as before. Again, it would be nice to have the scaling of the underlying trend, but in practice that doesn't work. The models just become unstable, even if you can write down the equations. You have an underlying trend which has got a drift, which is linear, and is subject itself to a second order shift in the drift. And the second order drift has got a mean regression process. So what happens is basically you are drifting along, you have a particular trend, and the trend itself is occasionally being hit hard by something, okay, with a mean regression factor which we don't know. The noise here we've just assumed is Gaussian for reasons explained. More interesting is this thing. And again, this is where, among many other reasons, using a probabilistic programming language like Stan helps you with, in comparison to out-of-the-box standard models. So in this, we thought about things here. Now, because it's in Stan, we need a continuous distribution. Okay, I originally thought of using a Poisson process here, but a Poisson process has bad properties for current purposes. In the end, I used a modified Cauchy process, but I had to be quite careful because, interestingly, if you hit the thing too hard, if you have it, if you move along and you hit it hard and then you let it stabilize immediately, the model shows less good convergence properties than it would otherwise do, which is a good indication that you're not getting it quite right. Okay, so that's what we did. And after a couple of experiments, this was the model. This is the complete model, again, written down in Stan. Theoretically, you could actually, almost all of this you could theoretically set up in a standard state space model package, solving for maximum likelihood using some sort of a Kalman filter. In practice, if you attempted to solve this model using a Kalman filter, I am confident you would fail. There's just too much going on. You would need to calibrate it. The calibration is too complicated, etc., etc., etc. So really a model, this is a purely practical observation. I don't have any theoretical observation, any theoretical arguments to back this up, but I think it would be very, very hard to get a model like this, to solve it without using a tool like Stan. Anyway, you set it up and you solve it, and this is what you get. Okay? And you fit it, and again, it looks very good. basically the fit looked like what we got with the Gaussian process. Okay. The difference, again, going back to, yes, is that we're now in a position, because we have a state space model, to extrapolate it. Okay. And we can extrapolate it like that. And that's what we get. Okay. What you can see is that for this model, the confidence bounds, well, I should say that extrapolation in this context is in some sense trivial, because basically it's just a missing variable problem. You just set up exactly the same model and you say, I don't know the following values, and the model will find them for you automatically. You don't need to do anything new. So you extrapolate it and you can see the confidence bounds widening up enormously. But what you can also see is that the extrapolations, so this, the green, sorry, not the extrapolations. These are the actual data, which we got afterwards, by the way. This is a pure out of sample test. The actual data afterwards is comfortably, for the most part, inside the one confidence interval, one standard deviation credible interval for the processes. So let's see. So this is actually how we did with respect to the historical data. What you can see, as I said, when I was looking at the original Gaussian process analysis for Brand 3 Germany, basically you're looking at a secular shock right at the end of the series. So there's no particular reason why that line should go anywhere. It's worth saying that if you attempt, as we also did, but I didn't have a slide to do it, to use a standard ARIMA extrapolation on the same data, I think this line goes down here. Most of them are the same. The problem with that shock at the end is that it completely knocks off any of the standard tools you would use for stationary time series analysis. Our big disappointment was this one. As you see, if we'd been allowed to run the line, if we got one more point of data, we would have been right down the middle of the 9-month trend for the sales in the US, which we missed. But other than that, we did pretty well. Okay, so I think I should probably stop here. I prepared an earlier version of this slide with a draft that said, what should I say here? And I decided not to replace it, because I thought I would just say a few basic words about the practice of dealing with problems like this as you actually confront them. We made lots of compromises along the way. What we tried to do was to stick with what I would call principled, unprincipled design decisions to get stuff to move forward. There was also lots of stuff that suggested itself that we didn't really have time to do. One of the things that we wanted to do early on and didn't have time, but would have done if we'd had an extra 4 weeks, is that you can see, and we could see in the analysis that for instance, Germany and the United Kingdom are in many respects similar, and Portugal and Spain have got are naturally bound together. There's a huge grey market in the products between Portugal and Spain. So one market is influencing the other, and you would get more model stability if you could put those together into one hierarchical model with everything kind of, resting on each other separately. And unfortunately, in the end, we simply didn't have time to build that hierarchical structure. But that would have been the next step if that time had been available. Apart from that, it was just frantic work. So I will stop at that point.
Thanks a lot for the very interesting talk and very mathematical talk. Are there any questions?
Okay, thank you very much for the interesting talk. So I have 2 questions. The first one is about the Gaussian process model where you were fitting. Maybe if you could show the slide again.
Sure. Now that I've got... You want to see the stand code?
No, just the fit. Yeah, this one.
This one, okay, yeah.
Yeah, so I was wondering about how confident you are about this fit, since around time point 20, it seems like the noise becomes very wide in comparison to how much the confidence interval is widened. So
that's a good question. I mean, it actually relates also to workflow in these things. What we had was a suggestive fit, which we used. We invested a lot of time in building a model. We're not building a model, but thinking through the precise dynamics of the model. And in the end, this is what we got. I should say that several models we did try, sketch out a few others and try them, and they simply didn't fit at all. I don't know if you've experience with these sorts of Monte Carlo systems, but what happens is the thing just doesn't stabilize. It does not find its way to the typical set in technical terms. Yeah. So you can see to a certain extent, for these complicated models, if you can get the model to fit and get good metrics for performance out of it, that's generally a good indication in my experience. Yeah. More than that, I can't say.
Yeah. And my second question was about, so I can see it's very hard to fit this very small data set.
Correct.
So I was wondering if you were considering data augmentation to add some extraneous variables such as economic variables or some other variables that could correlate with the trends that you see.
No. My experience is that, for starters, I find such activities, unless you're very, very careful, methodologically unsound, because you can't just go fishing through data for extraneous data. We actually got data for various things as part of the project. So we got things like field sales spend and stuff. And trying to build that into the model in any way that acknowledged the structure of the underlying process turned out to be impossible. It's extremely hard. I mean, if you get it, that sort of thing, even when it works, mostly works if you've got simple correlations between external data and stuff. That is not remotely relevant in this case. I mean, I forgot to mention when I was saying it, a core point of this sort of work is that in the end, a large part of the data you take is expert knowledge of the dynamics of the data. It's not actually the numbers. If you have a time series of 70 or 60 points, then without getting information somewhere else, you're just not going to get anywhere. So the classical model of here's a table of numbers, fling it over the fence and see what you can do is a complete non-starter in a project like this. I mean, a large part of what you do is you're trying to figure out from experts what's actually behind the thing. Yeah. I mean, these are generative models. I think generative modeling is important for this sort of thing. Yeah.
Okay. Oh, there are quite a few more questions.
First of all, thank you for the talk. Just continuing the question. I can continue.
It's okay. I mean, I can multitask.
Okay.
Yeah, I'm good.
So, I mean, I think it's not the proper way just to fit noisy time series and for those outliers we see and just to make a fit which is not maybe good. Before that, there are some ways to deal with these outliers, for example, weighting, and for shorter time scales, just averaging. This is there's preparing some data segmentation.
Well, there's only 70 points in the series.
Yeah, but for example, 3 points. For example, let's say positive, negative, and average one. You can just average.
Sure, you could do that by putting an autocorrelation structure into the model.
More smooth. And this was just the first, not question, just the comments. And for the question, here I see that this is like a fit of three distributions around minus 15, around 20, and around 45, for example, with special height and width. So, I mean, for the next prediction, I think this can be done based on, like, assuming that there are three distributions for some reason, I don't know, and there will be some horizontal shift, and also the height will be based on those three heights of three distributions. Like, did you check that?
No. I mean, part of the point is that in projects like this, I mean, apart from the fact that you're welcome to try, although I think you'd run the risk of overfitting. With a project like this, this is all done to a very short time scale. So what happens is you build something, it works, you move on. There's always other models you could try. So I cannot say for other models, no, they wouldn't have worked.
I mean, maybe just only for this model it will work because it's different from slide 15, I think, if you move. Or here, for example, for top right, also free distributions is seen, but for example, for others not, but maybe there are different ways.
Okay, to be honest, just looking at it and saying I see 3 distributions, when you're looking at this sort of small data set, is a very dangerous way to proceed. I mean, the motivation, the underlying method here is to build a generative model on the basis of expert understanding of how the market functions. Okay, so for us, an important insight was where'd it go? Was discussing this with the people who understood the sales dynamics of these sorts of products in the market. It was when we saw that, I think, secular shocks to a trend in sales.
Yeah, of course.
And then
hidden information needed.
Yeah, and then what we did in this is to fit a model saying secular shocks to a trend in sales.
Yeah, I see the parameter.
Yeah, and the question then is how sharp the shocks are. So in a sense, we are already reflecting the what you just said about different distributions. What we got is straight line, bend, straight line, bend, and the general model fits that from that point of view. But then it's motivated by an underlying understanding of the dynamics of the market, rather than just eyeballing the data.
Thank you.
Okay, I think we just have time for a very short question.
I'm sorry, I'm also gonna hijack the microphone. I'm now one of the organizers, and I would like to encourage you all to take a look at our hitchhiker guide to the conference, where we discuss the difference between comments and questions, and we encourage you to ask questions rather than to make comments, and also, of course, to approach the speaker after the talk if you want to discuss anything further and make all of your comments. And I would like to ask, though, you said you were using STAN, so do you mean which the inference algorithm? Do you mean HMC, which is what?
Sorry, I didn't understand that. Say that again.
You said you were using STAN.
STAN, yeah.
STAN rather than Kalman filter, for example.
Yeah. And
I wanted to understand what do you mean by STAN, as it's not an inference, it's not an algorithm by a language, and what's kind of
STAN is an advanced Hamiltonian Monte Carlo simulation system.
Okay.
Yeah.
Thank you.
So you can program all these things in STAN. It's a general tool for building.
It's doing agency under
I don't really
It's using HMC as an inference method, right?
No, it's not.
Okay.
Okay, I think the time is over. I can see there are more questions.
Feel
Please
free to ask me.
Just come to the speaker, and let's thank the speaker again. Thanks a lot.